And we're on. I don't know why I keep saying that. All right, here we go then. So what we're looking at, we're going to work to this thing called free radical substitution. Okay. Now it is, as someone will tell you, it is a mechanism. And a mechanism just tells us what happens in a chemical reaction, tells us how a chemical reaction takes place. Reaction, oh, that's not good, takes place. Okay, that's all it is. Now we've got to learn a few things though before we do this. Okay, now the first thing we've got to understand is bond fission. Okay, and there are two types of bond fission. One is called homolytic. All right, bond fission. And the other one is called heterolytic bond fission. Okay, there's two types. Now we're going to, first of all, we're going to look at homolytic, and we're going to look at the example of a bromine molecule. There we are. And then we're going to look at the heterolytic. Poor old Axel is probably pulling his hair out now. All right, so here we go. This is a bromine molecule. I'm trying to make it nice and pretty here. Okay, there. So are we okay with that, both of you? You good with that? So far, so good. Excellent. So I've drawn an H. Yeah, sorry? Excellent, yeah. Actually, I imagine you're good for pretty much all of this, actually. Oh, okay, good. If I'm going too fast, just stop me, all right? So what we have in bromine. Now, bromine can split up, okay? And I'm going to give you the quick version, I think. Okay, bromine can split up in two ways. Well, it can actually split up in three ways, but two of the ways is exactly the same. And HCl can split up into three ways. Okay, now bromine can do this. It can just split apart evenly. If it's even, if each bromine gets the electron that it had originally, or it just gets an electron back, we say it is homolytic fission. In other words, homo means the same, lytic is to split. It splits the same. So if bromine does this, this is fission, homolytic fission. If bromine does this, we get these two guys, basically bromine atoms. Now these bromine atoms are known as free radicals. Okay, and what determines a free radical? They have an unpaired electron. That means one electron. Okay, so the way we show that, all right, the way we show it is, where's my pen? Is Br, and we put a little dot there, and that dot represents the unpaired electron. And these things are free radicals. Okay, you good with that? So far, so good? Azim? So, are you writing this down? Don't forget, guys, I'm going to post it on YouTube, so you don't have to. You might miss something, but it doesn't matter. All right, so don't worry, honestly. But I know students like to write things down, and I must admit, if you write things down, it kind of goes in your brain. So go for it. Eh? So the other type of bond fission is this, and this happens if one of the atoms gets the bonding electron and the other one doesn't. Okay, and if this happens, we don't get free radicals, we get ions. Okay, as you can see, the one on the left is going to be a positive ion, and the one on the right is going to be a negative ion. So we get ions if you get this uneven split, and this uneven split is known as heterolytic fission. Homo means the same, hetero means different, yeah? So if it's homolytic fission, we get free radicals, nothing's charged. And if we get heterolytic fission, we get ions, you get a positive and a negative. Now, we can see the same in HCl, okay? And HCl can split up in three ways. There's one way, I'll write the other one down here because I've managed to squish them up too much. And there you go. There's 3 ways HCl can split up. So let's go through them. One way is like this. You get, let's have a different color there. You get homolytic fission. Okay. One way, another way I should say, you get heterolytic fission. And the other way, the last way, you also get heterolytic fission. Okay, 1, 2, 3, 4, 5, 6. Okay, now obviously this first one is homolytic, and these other 2 are heterolytic. Okay, I'm going to slow down in a minute, guys. I just want to get this done, and then I'll see where you are. All right, so if you get the homolytic fission, you see we have a hydrogen free radical and a chlorine free radical, and these are free radicals. And that's what you would get if you got homolytic fission. If you get heterolytic, there's 2 ways it can split. The hydrogen can lose the bonding electron, so you get H plus and Cl minus, or the hydrogen can gain the bonding electron and you get H minus and Cl plus. Both of these ways, these 2 here, where you get ions formed, are known as heterolytic fission. Heterolytic fission. And obviously, if I get heterolytic fission, I get ions formed. So I'm going to stop there briefly. Are you both okay with that? Go for it. What? No, to be honest with you, I haven't really finished this yet. I hope it will become clear, right, when I finish. All right. All right. But so far, so good, kind of. All right. All right, excellent. So homolytic fission means they split evenly, and heterolytic fission means they split unevenly. So this is specifically for azime because I think Axel knows this. What type will? Oh, I see what you mean. This thing at the top. That. Oh no, no, they're just titles. Don't worry about those. No, no, no. This, what? No, no, that's all. So I'm so sorry. Well, actually, annoyingly, it is what happens, but that's not intentional at all. Okay, I should have said this. Bond fission is either homolytic fission or heterolytic fission. They're just titles, but annoyingly, you'll see. All right. So if you look at the left-hand side, you see the bromine molecule. As in, what do you think it's most likely to do? How do you think bromine is most likely to split? Now, don't guess. Is it going to be homolytic fission or heterolytic? As a kind of a thought. Yeah, why do you reckon? E- exactly. You've just exactly, and they have the same electronegativity, don't they? All right, so you're exactly right, and that's exactly why I asked you. So bromine is this one is a tick. It does homolytic, and it doesn't do heterolytic. Okay. Now, why is that? Because a bromine is a bromine, and they have an equal pull on the electrons, so they're just as likely to share, aren't they? All right. Now with heterolytic, sorry, with the HCl, now, there is a difference now in electronegativity. The chlorine is more electronegative than the hydrogen. Have you done the electronegativity yet? So you understand that statement, yeah? So which way, I'm going to call them 1, 2, and 3. This is 1, this is 2, and this is 3. Which way do you think HCl will split up? Exactly. So you exactly know what's going on. So we're unlikely to get that. We never get this, but we're going to get this. And why are we going to get that one? Because, as you quite rightly said, chlorine is more electronegative than the hydrogen. And if they're going to split, the chlorine is going to get the electron. So well done. So far, so good. We're looking good. Okay. Now, I know this doesn't look like organic, and to be honest with you, at the moment there's no organic, but we have to lead up into organic. All right. So here we go. Right, now we're going to bring across the concept of curly arrows. Now, a curly arrow is one of two types. It's a full head. This is called a full head curly arrow. Okay, and you get a half head curly arrow. Curly arrow. Now, we use both of these in chemistry, but the full head means a movement of 2 electrons, and a half head means a movement of 1 electron. Okay, now you won't know how we're going to use these at the moment, but I promise you, if it's a movement of 2 electrons, it means the bonding electrons goes to one atom or the other. And if it's a movement of 2 electrons, we're going to end up with ions formed. So you're going to get ions formed when you have a full head curly arrow. Okay, you won't know what that means yet. All right. If you have a half head curly arrow, you're going to get free radicals formed. All right, free radicals formed. Okay, so there you go. So, since the first mechanism we're going to do is called free radical substitution, we're going to use half heads. Okay, now let's use them in a nice, easy way to start with our examples we've already done. We've got bromine, and we've got H, and we've got Cl. Let me put my electrons in again. I'm quick with electrons. I'm sure I'm faster than you two, but I've been doing this for millions of years, so don't worry about it. All right. So when the first one, the top one, let's see if I can use shift. Yeah, there you go. There we get a nice arrow. Oh, that didn't work. And then I get a nice arrow there. Okay, so the bromine here, I'm going to get 2 bromines, and here I'm going to get an H, and I'm going to get a Cl, and this gets its electrons, and this gets its electrons. The chlorine gets its electrons here, and the hydrogen loses its electron, so we get a plus there, and we get a minus there. So are we so far so good with these 2 diagrams? The top one is going to be homolytic, and the bottom one is going to be heterolytic. All right, now let's use the curly arrows. What color shall I use now? Orange, I think. Now, one of these electrons goes on to there. Oh, well, let me do that again, because the way I've done it is weird. All right, let me do that. We say this electron goes there, half head curly arrow, and this electron goes there. And we end up with 2 free radicals. We could write these as Br dot and Br dot. So far so good? So that's the use of half heads. And now the full head, both electrons go onto the chlorine. That's a full head curly arrow. These 2 are half heads, 1 electron. This one is a full head, 2 electrons. And that's why we get heterolytic and homolytic. And this is why we get free radicals. And this is why we get ions. So I think we're all good there. We're all caught up. Shall I slow down a bit? Are you sure? All right. No, yeah, don't worry. Honestly, I will slow down if you need, if you think so. Right, now we're going to do a reaction we did in Form 5, and the reaction is with methane, and we're going to react it with chlorine. Okay, so first of all, I'm going to do the reaction. This is CH4, We react it with chlorine and we get CH3Cl and HCl. All right, this is a Form 5 one. You may have forgotten it. It doesn't matter if you've forgotten, but it is a Form 5 reaction. So this thing here, the thing we get is called chloromethane. Okay, and obviously we get HCl. And if you remember your Form 5, this happens in sunlight. Okay, and we called it in Form 5 a substitution reaction. Why did we call it a substitution reaction? Because one thing went on and another thing came off, like in football, substitution. So how do we do this then? Well, believe it or not, let me do that a bit nicer. That's awful. If we have a jar like this, okay, and in the jar, if I've got methane and chlorine, and I expose the jar, I expose the jar to ultraviolet light. Now in Form 5, we used to call that sunlight, and sunlight has ultraviolet light in it. Okay, but in Form 6, we tend to use the term ultraviolet light. If you don't do physics, let me spell it for you. Ultraviolet light. Okay, so we use ultraviolet light, and again, if you're good at physics, ultraviolet light has just the right energy to break up a chlorine molecule. So if we expose methane and chlorine to ultraviolet light, we get a big bang. We get a big explosion. And these two react together, but you will get an explosion. Okay, so far so good. Axel, to be honest with you, Axel, I'm not at all worried about you because I know you know this stuff. All right. So, so what I mean, Axel, you don't have to answer unless it's a no, Axel. All right. But Azim, you've got to answer, I'm afraid, because I got to know. So you're good so far, Azim. Have you learned? It must have been. Oh no, let's not say the teacher. No, we can't say the teacher because this is going on YouTube. Eh? So, all right. So let's move on. So far, but you understand what I've done so far. Excellent. All right. So now, well, we're going to do what we call the mechanism. Okay. So this is the free radical substitution mechanism. This is what's going on. Okay. Now, the first thing that happens is a chlorine, there's a chlorine molecule, gets zapped with ultraviolet light and it splits up homolytically. So, oopsie daisy. So there it goes. And if it splits up homolytically, you're going to end up with two chlorine radicals. This is a chlorine radical. Okay, so you get two of them. So that's the first step. The second thing that happens is a methane molecule, here's a methane, will now interact with one of these chlorine radicals in another homolytic bond fission. There's one electron from here goes in there, and one electron from the bond goes on there. So this is going to give me CH3 radical. This is going to be a radical, and HCl. Okay, so this is known as a methyl radical. And the HCl is there. That's where the HCl comes from. Okay, so there you go. And the last thing that happens, as you can probably see, is this methyl radical, this guy here, is going to, oh, no, let me not put a plus there, but it's going to come across the other chlorine radical and this electron is going to go between them, and this electron is going to go between them, and we're going to get a bond formed between the C and the Cl, like that, and we have our product, which is chloromethane. So how is that? Is that okay? Okay. No, it doesn't. The chlorine radical breaks up the CH bond, this thing. Exactly, that's exactly it. It goes over to the methane and it steals its hydrogen away. Okay. Uh, yes, yes. Well, it's more electronegative than both. So it will steal both. It will do that exactly because it's more electronegative. So very well done. Okay. Now, the first stage, the first stage, believe it or not, is the only stage where ultraviolet comes into it. Crazy but true. Okay. Now, the first stage is which starts everything off. And the first stage, because of that, is known as the initiation phase. The second phase, it keeps the reaction going. So this one is called the propagation phase. And the last thing, two free radicals kill each other to form the product, and this is known as termination. This is the termination phase. So to recap there, if you've got no free radicals and you make some free radicals, that's initiation. If you've got a free radical on the left and it produces another free radical on the right, that just keeps everything going. That's called propagation. And if you have two free radicals that kill each other to make the product, that's termination. All right. Now, I'm sure you can see another termination step here. And the simplest one, I think anyway, is this. A chlorine free radical meets another chlorine free radical. They come together, and these guys are going to form chlorine. They're going to reform chlorine. And what type of phase would this be? This would also be termination. There's another termination step where a methyl free radical meets another methyl free radical, and one electron goes there, the other electron goes there, and what do we get? We get CH3, CH3. In other words, we get ethane. Isn't that crazy? Isn't that nuts? Ethane. And that is another termination phase. Are we good? Yeah, you can get those things happen as well, eh? Ethane, yeah, that says ethane. It's my handwriting. Yes, you do. You get ethane. Now, it's a good question though, because you think, what the hell's that doing there? You'll get this in very small amounts. Now, when we get things in very, very small amounts in chemistry and in physics and stuff, we say we get them in trace amounts. So it's so small, we say, it's trace. Now, Azim, I'm pretty sure I asked this to Axel last week, how do you prevent ethane being formed? Oh, either the microphone's gone or there's. Well, all right then, it's a bit of a mean question. You've got to prevent what from coming into contact with each other? Exactly. So what we've got to do is we've got to prevent these meeting, haven't we? Prevent these from meeting. Now, In other words, you want them to react with a chlorine free radical before they meet each other. Does that make sense? And it's done easily in chemistry, this. I know it's hard to think about it, but the way we do that is we simply use excess chlorine. Does that make sense? And that's honestly, we often say you use excess this, excess that, but in this particular case, there's a big reason for it. We use excess chlorine, so we prevent ethane forming. But it will form, eh? It will form if you're not careful. Well, you know what? If you've got a billion zillion molecules floating around, you're always going to get some bumping into each other. Do you know what I mean? I don't think you can ever not make it, but you can have it in such small amounts that it doesn't matter. All right, so you're good. So this is a free radical mechanism. So you have an initiation, propagation, and then termination. And there are other termination steps here, as you can see. Are you good with that? All right. Interestingly, oops, Lizzie. Interestingly, there's another propagation step. You don't have to know all of these because there's loads of these things. There's honestly, these things go on forever. But this is a possible propagation step as well. CH3 propagation. Remember, it means a radical is on this side and it's going to react with a chlorine molecule. So what perhaps could happen here? This electron goes there. One of these electrons goes here. The other electron goes on there. And what am I going to get? I'm going to get this guy plus a chlorine radical. Does that make sense? Yeah, no problem at all. Axel, you're right. I don't think I did that one with you last week. Okay, yeah. That's a possible. What would you class that as if you had to class it as something? Is it an initiation, propagation, or termination? Oh, no. I know it could be a termination, couldn't it? Because you get the product, but it's not. Because on the left you have a free radical, and on the right you have a free radical. In other words, this keeps the reaction going. So this is a propagation. It's only a termination. Excuse me. It's only a termination when two free radicals kill each other, and then you get the product or something. Does that make sense? Yeah. They're going. This is not very. You're quite right to mention that. There's a carbon, and there's the hydrogens, and there's the chlorine. Now we say the electrons come in there and there. Okay, and when you get two electrons between the carbon atom and the chlorine atom, that's what forms the new bond. So does that make sense? Okay, good. So we're all good there. Yeah, I guess we're good. Okay, Azim, are you not all right? Now let's have a quick look. Everything's good. It's a nice bit of chemistry, though, isn't it? So, Azim, are you saying you haven't done this yet, or you've done it but you didn't understand it? Oh, all right then. But you've done chlorine plus methane. All right, yeah. I go a bit far, I must admit. But the way I do it, I like to do it this way because I understand it this way. This is how I understand it. Now, if you look at your textbook, okay, it will do